spacecraft to be
Hello,
launched
today I'm going to
from a
present
space
chapter 7 Particle
shuttle.
Motion in Space. Kepler's laws. People have studied the motions of planets since ancient times. First, it was believed that Earth was the center of the universe and that the Sun and other planets revolved around it in perfect circular path. This was known as the geocentric theory. Later, it was discovered that they traveled in epicycles. And in 1543, Copernicus invented the heliocentric theory, which stated that the Sun was the center of the universe and every planet revolved around it. Kepler's three laws of planetary motion. First law: each planet travels in an elliptical orbit around the Sun. This states that the planets orbit are ellipses rather than circles, as it was believed before. Kepler's second law: an imaginary line drawn from the Sun to any planet sweeps out equal areas in equal time intervals. Third law: the square of planet's orbital period, t squared, is proportional to the cube of the average distance between the planets and the Sun, or t squared. We can see this in the equation t1 squared over t2 squared equals to r1 cubed over r2 cubed.
We're going to look at Kepler's three laws. The first law is a statement of how the planets move. The planets move in an elliptical orbit. The Sun is at one focus of the ellipse. So the path any planet takes around the Sun is in the shape of an ellipse. And an ellipse has two foci. The Sun is at one foci. This works for any system. So if an object is going around the Earth, the object will take a elliptical pattern, and there'll be two foci for that ellipse, and the Earth would be at one of those. So the first law is just basically saying the planets don't go around in a circle, which is what everybody believed at the time. Let's look at the second law. Kepler's second law is an observation. He noticed that a straight line joining the Sun and a planet sweeps out equal areas in equal intervals of time. What that means is, if it took 1 month for the Earth to go from here to here in its orbit, it would take 1 month for the Earth to go from here to here in its orbit. And he noticed that this area was exactly the same as this area, which meant, since this line was so much longer, that this didn't have to be quite as long for the areas to be equal. So as a result, the planet must be going slowly here, but quite a bit faster there. So the law is about the areas being equal for an equal period of time. But the understanding is that what it means is that the planet is speeding up and slowing down in its orbit in order for this to happen. And he didn't understand why this was. But the important thing was, it showed that there is some kind of relationship here of the planet's orbit around the Sun. And so there must be some mathematical relationship that someone will figure out, and that someone was Newton. Kepler's third law is a formula. The formula is K is r cubed over t squared. What the variables are, K stands for Kepler's constant. It's in meters cubed per second squared. R is the mean radius of orbit. If we have the Sun here and the Earth going around the Sun, or any planet going around the Sun, we already said it goes in an ellipse, so the radius is going to change. So we use the mean radius to do this calculation, and it's in meters. T is the period of orbit. That's the time it takes the planet to go around the Sun once, and that's got to be given in seconds. So for a system like the Sun, with the Sun at the center, we have a constant, 3.35 times 10 to the 18 meters cubed per second squared. So any planet follows this relationship. What it means is there's a relationship between how far the planet is from the Sun and how long it's going to take to go around the Sun. This formula is good for any system. If we use the Earth at the center, the object in the center controls the system. Just like the Sun, you could say, controls our solar system, so we have one constant for it. If I put the Earth here, and I have the Moon going around the Earth, or any satellite, it must also follow this law. But the constant will be different. Because the Earth is at the center, it'll be a constant based on that system, and it would be a different number. Just like if I had the planet Jupiter, objects orbiting the planet Jupiter, if we put a satellite or there's a moon around Jupiter, then it would follow this law, but it would be a different concept.
Kepler's third law describes orbital periods. The constant of proportionality between the variables t squared and r cubed is 4 pi squared over g m, where m is the mass of the object being orbited. This gives us an equation that t squared equals 4 pi squared divided by gm times r cubed. We have the two equations for the period and the speed of an object in circular motion, in circular orbit. T equals to 2 pi over the square root of mean radius cubed over constant times mass of the object. Then we have the equation for the speed of an object in circular orbit, which is Vt equals to square root of g times m over mean radius. Now we're going to solve a problem involving the equations just learned. Sample problem D. The color-enhanced image of Venus shown here was compiled from data taken by Magellan, the first planetary spacecraft to be launched from a space shuttle. During the spacecraft's fifth orbit around Venus, Magellan traveled at a mean altitude of 361 kilometers. If the orbit had been circular, what would Magellan's period and speed have been? Given R1 equals 361 kilometers, unknown T and Vt. So from the table we know that Venus, the mass of Venus is 4.87 times 10 to the 24th power. The mean radius is 6.05 times 10 to the 6th power. And the distance from the sun is 1.08 times 10 to the 11th power. So now we choose the equations we have, which are t equals to 2 pi times the square root of r cubed over gm, and vt equals to the square root of g times m over r. To find the distance from the spacecraft and Venus, we add the radius of Venus and the distance between the spacecraft and Venus and the Venus radius, and we get that it is 6.41 times 10 to the 6th. Then we just plug in the values as seen in the slide, and we get that the Magellan takes 94 minutes to complete one orbit. As we learned in the previous chapters, weight is defined as the magnitude of force due to gravity. A scale does not read weight unless no other force other than gravity is pushing downward on you.